Let's take a look at 2016 E&M number 2. This is a circuit. That arrow through our battery tells us that this is a variable power source. We have an ideal voltmeter up here in parallel with a resistor. An ideal voltmeter has infinite resistance so that no current goes through it. All of the current goes through the resistor. We have a wire sample over here. That's just going to be another resistor. And we have initially an ideal ammeter. Later on they're going to change that. An ideal ammeter, which means it has zero resistance and it does not affect the overall resistance of the circuit and therefore the current. All right, part A. How does the current through the wire sample compare with the resistor? Well, as you walk around the path, there is no option but to go through both the resistor and the wire sample, which tells us that these guys are in series. And things that are in series have the same current going through them. The voltages can be different, which brings us to part B. How does a potential difference compare? Well, it depends on the resistance of the sample. Remember the Kirchhoff loop rule. Add up all the voltages around the loop and you end up at zero. So you go up through the battery, which is like a ladder, down through one resistor, which is part of a slide, down through the other resistor, which is part of the rest of the slide. And the relative sizes of the slides depends on the relative resistances. So we have battery minus resistor minus wire sample gets us back to zero. These two guys depend entirely on, well, how big is the resistances. So if this is a small resistor, most of the voltage drop will come through the resistor big R. But if this wire sample has a big resistance, then it is going to have most of the potential energy drop. All right, part C. Well, we want to graph a straight line. So for part C, our graph of our straight line based on the information that they've given us is going to be V equals IR. This is going to come out of Ohm's law. We can already figure out what the current is through this guy because it's given to us. Those two currents are the same. The point of parts A and B is to get you to think about Ohm's law and Kirchhoff's loop rule so that when you get down to here, you've already thought of V equals IR and you can start thinking about how am I going to graph it to get a straight line. So what we want is for this to be applied to just the wire sample, where the value of the wire sample is going to be our slope of our line. This is going to be X, and this is going to be Y. Well, in order to get the voltage drop across that, come back over here to the Kirchhoff loop rule. The wire sample voltage is going to be the battery minus whatever was taken up by the big resistor. So hey, look at this. They gave us the battery and they gave us the voltage drop across the big resistor. So we can calculate what the voltage drop across that, and that's going to take up one of our columns. We're not going to need the other column here. So the horizontal axis, we're going to say that's just the current. And for the vertical axis, what we're going to do is we're going to subtract the two voltages that we have, and the leftover voltage is going to be the voltage drop across our wire sample. So you pull out your calculator and you subtract those things, and we're going to get, for this column, which we're going to label, I'm going to subtract it, E minus V sub R. We have 0.071, 0.165, 0.23, and 0.33. This last column we don't need to use. Now I'm going to pause, clear all this stuff out so that I can scroll down and take a look at the graph. All right, everything cleared out. Let's zoom in on the graph so that we can use this grid that they have provided for us. And what we're going to do is we're going to have to set up our axes. Notice how in the directions they say clearly scale and label all axes including units. And we're going to plot the points and then we're going to draw a straight line. They're telling us how they're going to award and distribute points on this part with all of those directions up there. So we already said that what we want is the voltage drop across the wire sample, and we want the current through the system. That's measured in amps. And what we need to do is set up our scale such that when we plot our points, it takes up most of the scale. So we're going to put 0 down here in the bottom left-hand corner, and we're going to count by 0.2s for the major grid lines across the bottom to make sure that we use up most of this, because our maximum current is 0.67. So our maximum current is going to be somewhere between these two lines over here. And for the voltage, our volts need to go up to a little bit above 0.3. So for the voltage up the left side, that's a 2. We need to make sure that we can plot all of our points. We don't go off the grid, but neither do we want to only use up a tiny amount here. Now, what does that mean for our minor grid lines? Well, across the left side, that means we're counting 0.02s, and across the bottom, we're counting by 0.04s. Now, this works out nicely because the currents that they've given to us are very nearly going to be multiples of 0.04. So as we plot our points, we're going to go over to 0.6 and up to 0.7, 0.16, and then 0.07. And then we're going to go over to 0.32 and up to 0.165. So 0.165 and 0.32, 428, so over about there. And then we're going to go over to 0.49, so if that's 0.48, and then we will go up to 0.23, so in this space here, and then we'll go up to 0.68, over to 0.68, and up to 0.33. So right about there. Next thing they told us is that we need to draw a straight line. Now, on my computer system, this is going to be somewhat difficult, so we'll see how well I do here. All right, that was poorly done. Let me try again and make this a little bit steeper, because once we draw a straight line, all right, now that's not steep enough. All right, I'll give this one more try, and it took me a few tries to get an almost acceptable line. And I've marked 2 points that I will use from the line. Keep in mind that you're using points from the line, not your data points, to calculate the slope for part E. So slope equals the change in y variable, which in this case is voltage, over the change in the x variable, which in this case is the current. So we have 0.38 minus 0.1 over 0.8 minus 0.2, and this gives me a value for the slope of 0.46 repeating, which rounds to 0.467, and that's volts per amps. Now, going back to the equation, VR equals IR, where this guy is Y, this guy is X, that makes the resistance the slope. So R equals 0.467, and that's going to be in ohms because that's how we measure resistance. Now you need to have calculation of slope using points from the line, not points from the data table, and you need to clearly indicate that the slope and the resistance are the same thing, and of course you're going to have units on the numerical answer. for part F, wire sample, what's the resistivity? So the resistivity is going to be measured relating the length of the sample over the cross-sectional area of the sample. Resistivity, that's this rho symbol, and that will give us the resistance. Well, now we know what the resistance is. That's 0.467. Whatever value you use, that will, or you get from your slope, from your hand-drawn graph, will go here for the resistance. They give us length, and they gave us the radius, and in this case, the area is going to be pi radius squared. Don't forget that you're going to be squaring the times 10 to the minus 3 also. So rearranging this guy, we will get resistance from the previous part, cross-sectional area over length. And when we plug in these numbers, let's see here, we should get resistance is 0.467 times pi times the radius squared, and then divide by the length, which in this case is 3 meters. And I got 4.89 times 10 to the minus 7th, and that's going to be measured. If you take a look at the units here, R is in ohms, and area is going to be meters squared divided by meters gets us times meters. Now, obviously, your answer will be a little bit different based on whatever your slope is from your hand-drawn graph. For reference, the answer key has a resistance of 0.53, but they allow that the linear regression from these guys is, using a calculator, going to be 0.49, which means that the resistivity is going to be 5.51. So my values are a little bit off because I had to hand draw this on the computer. Now I'm going to have to pause again and scroll down a little bit farther in order to be able to look at part G. All right, G part 1. Suppose the ammeter is not ideal. If the ammeter is not ideal, then that means that it has some resistance. Not ideal ammeter. That means it now has resistance. If it has resistance, then we have increased the overall resistance of the system. So R measured is wire sample plus resistance of the ammeter. So the overall resistance of the wire sample is actually going to be less because it's only part of the overall resistance. So we're going to say less than, and this is our reason. The measured resistance is including the resistance of the ammeter, which once you subtract it out, now you're going to get a smaller number. All right, part 2. The ideal voltmeter is replaced by a real voltmeter. Will the readings be greater than, less than, or equal to? Well, they are going to be greater than. And once again, a real object, as opposed to an idealized one, is going to have an incorrect resistance. For the ammeter, that means now the resistance is not 0. But for the voltmeter, it means now the resistance is not infinite. That means that now our circuit looks like it's 2 resistors in series, in parallel, where this one is the voltmeter and this one is R. That reduces the overall resistance, which is going to reduce the measured voltage. So the ideal voltmeter, which allows no current to go through it, is going to measure a greater voltage than the real voltmeter that has an incorrect resistance.